Okay, so we are... The ideal gas law, PV equals nRT, is really easy to use, gives you nice predictions and things. However, under certain conditions, it doesn't work so well. And the problem is that, well, we're going to get into what the problems are, but that's really all the ideal gas law is meant to be, is to give you ballpark figures. It isn't meant to give you real-life answers. And because life is more complicated than what the ideal gas law states. And the word ideal is kind of the big hint, I guess. I might as well tell you. What is an ideal gas law? When they say that a gas is acting ideally, that means it's really acting like what? Does anybody know? What's that? That's true. Ideally, the equation will work, but they're just dots. And you don't see that. All we see is PV equals nRT, and we use the equation to predict pressure, volume, moles, or temperature, right? But the underlying math of all this is that they're not molecules, they're just dots, is what an ideal gas is. Dots, mathematical dots, X, Y, Z in space, dots flying around. Well, can dots collide? But it doesn't have any volume. There isn't any mass. It can't. How could it? It's imaginary almost. It is. Well, it is imaginary. They can't collide. They don't have any volume. They don't have any mass. They don't even exist. It's just a mathematical dot in space is a molecule. So you bet. I mean, gases don't behave that way, right? So I think under any conditions, when gas molecules act like dots, in other words, it doesn't seem like they have any volume, it doesn't seem like they're interacting, it doesn't seem like they're colliding, then it's going to act ideally, and PV equals nRT will give you better answers. But when things start under conditions where the gas molecules are interacting, PV equals nRT is going to be way off. Now, what conditions would that be? When would you get, because you don't want collisions to happen, right? Because that would be, then you can use PV equals nRT, they're acting like dots. Would that be high pressure or low pressure conditions? What would you imagine? Yeah, and you don't want them to collide, right? Because you want them to act like dots. Really low pressure, all right? If you want really low pressure, because then the odds are they're not going to collide, right? So maybe to use PV equals nRT when you're filling up a Michelin tire, I bet you the Michelin does not use PV equals nRT in all their equations and all their ways of designing tires, because that's not low pressure. They're going to use something else. We're talking about another equation here. How about temperature? This is the oddball. Would you think really high temperature or really low temperature? To avoid all this collision stuff. Really, what, Adelpho? Really low? I would guess really low too, right? Because then you think they'd have a lot less energy. The problem is when they collide, they start, things get cold. What happens to a gas? The C word, condenses. Man, they're really interacting there, and that's the total opposite extreme of ideal. So you want the temperature to be really, really high. That's kind of odd, because things are, but I guess it kind of makes sense because they're flying around so fast that they don't interact at all. Yeah, they're going to collide, but they don't interact. They don't stick together. So PV equals nRT, best bet when the pressure's really, really low and the temperature's really, really high. Then PV equals nRT works the best. But so a lot of manufacturers and guys, they're not going to use the ideal gas law. Pretty much only general chemistry students use the ideal gas law. Okay. So there's a new theory in town, the kinetic molecular theory of gases. And here are its main stipulations here, its ideas, its postulates. That gases are actually composed of molecules. Okay, well, that's a good step forward from dots, right? So that's nice. So that However, they're saying the molecules are really, really tiny compared to the distance between, that they collide. That's good. Molecules are tiny. And I guess number 2 kind of makes sense too, because they're not living things. I mean, they're just like miniature baseballs flying around. They should fly in straight lines, okay? But that's kind of odd too, right? Because if you have gravity taking into account, things aren't going to be going in straight lines. But that's what they're assuming. And in 3, forces of attraction, repulsion between gas molecules is negligible, except when they collide. So you have 2 of them flying by each other, they're not going to suck up. They're just going to keep flying by one another unless they actually collide. And then when they do collide, the collisions are elastic. Now, who's had general physics? Anybody? Nobody's had physics in high school. All right? Okay, now you had an elastic collision. You had to talk about it, didn't you? What is it? All right. It's like a what? Yeah, rebounding. There's no deformation, right? That's elastic. All right. I guess if these steel balls were made out of Play-Doh, that wouldn't. I should have that too, right? Because that wouldn't be elastic. That would be inelastic, right? So these are elastic collisions. So they're trying to say that, man, these molecules, well, they're like these guys, right? Collisions are elastic. Where does all the energy go in an elastic collision? It can't go into, right? Because these guys are flying together. Conservation of energy. Energy before equals energy after the collision, and during the collision, energy is conserved, right, the whole time. Can't be creating or destroying energy. Where does the energy go? We can kind of hear some of it. Yeah, these guys go bouncing off, but you can hear it. There's some energy goes into sound, right? But then a good portion of the energy, yeah, you're right, they're going to end up moving off in opposite directions, but they're not moving off as fast as they were when they were coming together. So some of the other energy, some energy goes to sound, some energy in this collision goes to, does anybody know? See if I can do this without hurting Yesenia here. Only the guys in front are going to be able to start smelling this. I can smell it already. I'll have to keep doing this. I'll end up hurting myself. But if you look closely at the paper, you definitely see heat, right? In fact, yeah, you can smell it, right? Burned, right? So it goes into heat. A lot of the energy goes into heat. It just doesn't go into reshaping the objects that collided. That's an example of an elastic collision. Okay. The average kinetic energy. Oh, there's one type of energy. Those folks who have had physics. There's all these different types of energy. There's electrical energy. There's potential energy. There's kinetic. What's kinetic energy? Ooh, Gloria, that's perfect. Energy of motion. So if something's not moving, does it have any kinetic energy? No. Has to be moving, right? So the energy of motion, the kinetic energy of gas molecules is directly proportional to the temperature. So you heat these gas molecules up, their kinetic energy increases, and they start doing what differently? Moving faster, right? And there's other types of motion besides flying in a room faster. Oh, jeez. They can start spinning faster, right? There are other types of motion. And if it was an actual molecule, they could start vibrating faster or something, right? There's all these different types of vibrational modes. But all that's kinetic energy, energy of motion. Okay. And I think I already showed you this, so I didn't bring it in. That balloon, and then I dumped liquid nitrogen over it, and the guy got smaller, right? And then all the liquid nitrogen evaporated or boiled off, and the balloon got bigger as the temperature warmed up. Okay, so we have a few movies here, very short, but you just need to fill in the blanks as we watch the movie. So there's our ideal gas law, PV equals nRT. And we're talking about, they're going to do a few experiments. So you're going to fill in the blanks as you listen to the experiment. Okay. Oh, thank you, sir. Let's see. Here's experiment number 1. Let's see if I can make this guy bigger. There he is. So you just got to listen and then fill in the blanks.
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder.
That was kind of fast. Let's do it again here so you didn't catch all that.
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder.
That kind of makes sense. I mean, you make that piston smaller, there's less space for the guys to move around, so yeah, they're going to collide more, right? So you got them, have them all filled in? Anyone need to hear it again? Here's the second experiment. So you might want to read it over first and so you know what your blanks you're filling in here. We now want the piston to create a constant blank and number of blank. You might be able to fill in some of them right now. Okay, here's experiment 2.
We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions.
Okay. Let's try it again here.
We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions.
So all of this is the kinetic molecular theory of gases. I mean, they're not dots. They're actually molecules colliding and speeding up as you increase the temperature, right? So you okay with experiment 2? All right. Read over the last experiment and we'll fill in the blanks. Okay.
With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions. With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
One more time.
With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
I wonder why it doesn't want to do. Okay. You notice you can play the game with the equation, right? If you double, keep all this stuff constant. If you double n, that's like multiplying this side times 2. Well, this side has to get doubled too somewhere. Either the pressure has to double or the volume has to double, right? So mathematically it has to work out. Okay. So this is what we're going to spend the rest of the period on. You just work with the folks around you and see if you can answer these questions. And I don't know if you brought your book, that might help. If you're not sure, just ask, right? I guess if you've got a smartphone, you can Google if you have a question too. Okay? But I think those animations gave you enough information to try to answer these questions. Okay? So just try to give it a shot with the folks around you, and then we'll call it a day.